who is an expert, and we are recording this evening. So if anyone has a problem with that, please let us know. In any event, he's a key member of Georgetown Village. He's an expert on climate change, and he has previously to the Cocktails Conversation and Community program given a lecture on climate change, and we're delighted that he's reprising that topic for us this evening. He is an applied mathematician. He's interested in the mathematics of physical systems. He has expertise in the area of mathematical modeling with an emphasis on computer systems. And luckily for us, he's currently focused on the mathematics of Mother Earth. He's the co-author of several books and more than 100 journal articles, and his most recent book is Mathematics of Planet Earth, Protecting Our Planet, Learning from the Past and Safeguarding the Future. I can tell you he's a member of several scientific associations, a well-respected editor, has a PhD in mathematics and physical science. And by the time we're finished hearing him again, I am certain that you will recognize that he is an expert among experts. And thank you very much again, Hans, for participating this evening, lecturing on the key topic of the environment and the climate in which we find ourselves. Please.
Thank you very much, Carol. And thanks everybody for coming and tuning in to tonight's lecture. As Carol said, I'm a mathematician by training. But I've gotten interested in climate and climate issues for the last 10 years or so, and have been working in that area together with some colleagues, including my son. So I gave the title in the form of a question, because many people ask me, well, what do you mean by climate? And what really is climate change? And then, of course, why should we care? So if I can get my screen to go. Yes. So here's a pithy statement from Ben Franklin, who was always able to find in a few words what he really meant. If you ask the difference between weather and climate, then his answer is climate is what you expect and weather is what you get. What does that mean? Well, weather is what we experience on a daily basis. So it is small scale, both in space and time. We're talking about something that happens over the next few days. Climate is large scale. So we're talking not days or months, but years. If you look at weather is really determined by the atmosphere. If we knew everything about the atmosphere today, we could pretty well predict what would happen next. And next being the next week, let's say, maybe 2 weeks. So let's say up to 10 days. Weather forecast is pretty reliable because we know what happens in the atmosphere and that determines our weather. So if we look at the temperature, we look at the humidity, at the pressure, and if we have enough data, we can pretty well predict what will happen in the next few days. Climate is different. Climate is a large-scale phenomenon. We are not talking days, we are talking years, decades, even centuries. And it's not just the atmosphere. The difficulty is a climate system is a very complex system which has various parts. Besides the atmosphere, there's the oceans, snow and ice and lakes. There's biosphere. How do we use the land? And what do humans do in this system? So climate is impossible to predict because the humans affect what will happen. So what we can do in the study of climate is develop scenarios. What if, suppose we release more carbon in the atmosphere, what will be the result? How will that affect our climate over the next 10, 40, 50, 100 years? So keep that distinction in mind. I will be talking mostly about climate, but climate interacts with weather. So what happens to climate will affect us here on Earth in the next few years. Here's a schematic. of what I mean by climate system. So I really think in terms of a system where lots of things happen. There are lots of participants. There is the land here, there's the atmosphere above it, there's oceans on the left, there are mountains with ice and snow, there are ice sheets that float off the mountains, there's oceans and ice on top of the oceans, and there are humans. Here they are. I hope you can see my cursor. So think of climate system as composed of all these components: atmosphere, oceans, ice, snow and ice, biosphere, including humans. And this system receives its energy from the sun. And that's the only source of energy. There are no other significant sources, let me say, because most of what makes us grow, makes us alive on the Earth, in the Earth system, is from energy from the sun. And what happens is the Earth is a ball that gets illuminated from the sun. At the equator, there will be more energy coming in than at the North and South Pole. So what the climate system does is it distributes this energy that comes in primarily at the equator and distributes it around the world, and it tries to find an equilibrium. And think of it in terms of eons. I mean, there are, you don't think in terms of years when you speak about climate, you really think about centuries, thousands of years, millions of years. So this process takes a long time to establish an equilibrium, and it is not stable. It is never stable. The next slide shows you what happens. This is a slide that shows the temperature in blue and the CO2 in the atmosphere in red over the last 400,000 years. So we are at the very end of this graph, at the right corner, at the right side. About 400,000 years ago, the climate started to oscillate. There were warm periods, here, 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 and today. And there were cold periods, there, 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 and here. So now we are in what we call interglacial phase. These are the glacial cycles that happened during the last 400,000 years. And we are pretty sure that this is an accurate record. So it's not stable in the sense that it is periodic. At least it has been over the last 500 million years, let's say. And the remarkable thing here in this slide is that the red and the blue curve are almost the same. Sure, there are variations, smaller variations, but the temperature and the atmospheric carbon dioxide concentration, CO2, follow each other closely. So one can be used as a proxy for the others. If the temperature goes up, the CO2 concentration in the atmosphere goes up. When the temperature goes down, the carbon dioxide concentration in the atmosphere goes down. And you can tell from this graph that going up is fast, going down is slow. So freezing takes a longer time than thawing. That's the bottom line here, right? So you see this pretty much throughout the 500,000 years that I have on this slide. Anyway, so somehow there is a mechanism that regulates temperature and the CO2 concentration in the atmosphere. Keep that in mind. This was the last 500,000 years. We're going to take a look at more recent times. This is in the Northern Hemisphere, the last 1,000 years, roughly. So from the year 1000 up to today. And you see, yes, there are variations. So we are now on a shorter time scale. There are still variations on the shorter time scale. And what is happening? So here it's pretty stable. Up to here, about 1850. And you see that all of a sudden the temperature goes up. The curve here, the red curve here, indicates these are measurements done with thermometers. The thermometer was invented in about 1750, 1760. So the previous recordings here were not done with a thermometer. They were done with other means, primarily tree rings, if you go back, corals, ice cores in the Antarctic, and as well as in Greenland, and some historical records. So there is a large collection of data that were not measured with the thermometer that enable us to reconstruct the temperature profile that you see here. And you see it's reasonably constant on average. So 0 is the average between 1961 and 1990. It's here, and you see that it was a little below, but it was pretty stable until 1850. So what happened in 1850? That was the beginning of the Industrial Revolution. And I remind you from the previous slide, if the CO2 in the atmosphere increases, the temperature goes up. And that's exactly what is happening here. So let's take another look at this later period since 1800. No, sorry, I left that slide out. So this is clearly related to the Industrial Revolution, when oil and fossil fuels in general were discovered and put to good use for a while. The atmosphere had to absorb all the CO2 that was generated. It had been stored in the ground before, and now it was released because we are getting this stuff out of the ground, and CO2 goes into the atmosphere. And the next slide shows you what happens. This is the greenhouse effect. On the left, you see what happened up to about 1850. Here's the sun. The sun radiates the Earth, sends radiation to the Earth. Here's the Earth. The Earth is covered with the atmosphere. And the atmosphere sort of shields us from, let's say, traps the sunlight that comes here, that gets distributed around the Earth, and then the Earth sends radiation back. Most of it escapes again into space. So this is sort of a blanket that is sitting around the Earth, and that keeps us nice and warm. If there were no atmosphere, the temperature here would be about 50 degrees colder, 50 degrees Celsius, that is. So right now it's about 18 degrees. If there were no atmosphere, the Earth would be minus 30-some degrees Celsius. Now, what happened with the Industrial Revolution was that we got the fossil fuels out of the ground, we burned them up, CO2 escapes, it gets caught in the atmosphere. And the radiation that used to go back into the atmosphere here still does, but much less. Most of the CO2 is caught, is trapped, if you wish, in the atmosphere. And that heats up the atmosphere. So, whereas before there was an equilibrium, what came in was used and most of it went out. Now, what comes in is used, gets trapped, and doesn't go out as much. So it's like your car parked in an open spot, sunlight comes in, the inside of the car heats up. That's exactly the same phenomenon. It's caused by trapping of greenhouse gases, as we call them, primarily carbon dioxide, but also methane, water, and some others. So they are trapped in the atmosphere, and therefore the Earth is heating up. And that's what we see in this picture here, right? It's heating up and doesn't stop. So how do we know this? Well, there is an experiment that has been going on since 1958 on the left of this graph on Mauna Loa Observatory in Hawaii. There was a Mr. Keeling, sorry, and you see here his name at the top, Keeling curve. This is Keeling's curve. He did an experiment on Hawaii, at Hawaii, as well as in Antarctica and also some other places, where he measured the atmospheric CO2 concentration. And he did it very carefully, the same experiment, hour after hour after hour. And he analyzed these numbers and came up with this graph. This was Charles Keeling. Charles passed away in 2005. And then his son, Ralph Keeling, took over. So the curve continues. And what we see is two things. One is there is a seasonal variation. Up, down, up, down, up, down, up, down. Up means more CO2 in the atmosphere, which is true in the spring and early summer. And down is less CO2 in the atmosphere. That's happened in the winter time, in the summertime, sorry. Because then trees absorb lots of CO2 out of the atmosphere, so there is less in the atmosphere. That was one thing. You see this up and down seasonal variation. And so it's exactly an up and a down and an up and a down per year. The other thing that we see is that this curve goes up. It started, well, in 1958, it was at 310. Before that, pre-industrial time, it was at 280. And right now, we're over 420. This graph stops in 2018. In 2018, we were at 406 ppm. That's the unit. Think of this as some measure for temperature. Currently, it's 420. So we keep going. Not only that, but if you look at, this is not a straight line. This is a line that curves up. That means that the increase per year is increasing. So if we continue like this, it will go up and up and up, which means the Earth will get hotter and hotter and hotter. So that's not what we want. How do we know this? Well, so this is scientific evidence. It's an experiment that has been going on. It's extremely reliable. Many people have worked on it, helped analyze it. So we're 100% certain that this curve is exact. This is what we see. If you go to the Arctic today, there is sea ice, which is a particular kind of ice. It's ice that is floating in salt water. So it's porous. It has lots of holes in it, let's say. You can measure the volume of Arctic sea ice. So this is Arctic means at the North Pole. So at the North Pole is an ocean, and in it are floating sheets of ice. It's brine and ice, essentially. You can measure how much there is, and here is a graph. Starts in 1980, 1990, 2000, 2010, 2020. Of course, it depends on the time of the year. There is more ice after the winter, at the end of the winter in April. There is less ice at the end of the summer in September. But the trend is the same. It goes down and down and down. And parallel to that, the same thing happens in September. So clearly, there is evidence that Arctic sea ice is melting. This is a verifiable, everybody agrees that these curves are exact, they tell the exact story of what is happening. If you look at Greenland, Greenland is like a continent. It's a big rock, as it were, that pops out of the ocean, Northern Atlantic, and is covered with ice. Now, this is not sea ice, this is ice. That means it's snow that has been falling over the eons and has turned into ice. So it's solid. It's about 3 kilometers thick in most places. So it's a humongous amount of ice, which contains a humongous amount of fresh water. So it's a source of fresh water, one of the largest sources of fresh water on Earth. And that water is trapped in the ice. But when the season heats up, some ice melts. And that's colored here in red. In 1992, it was confined to this southernmost area. In 2002, 10 years later, it was also still in the southern half, but it had also gone to the upper northern half. And if in 2007, it was even worse, then this whole thing was melted. So you can see the progression. I did not go beyond 2007. I could not find a similar picture, but the trend is clear. Greenland ice sheet is melting. And that means a lot of water is released. That water has to go somewhere, and it goes into the Atlantic Ocean. So it causes sea level rise. And the sea level rise is obvious in one of my next slides. Here is another picture. At the other extreme is the Antarctic ice sheet. And so this is the South Pole. And around the South Pole is a continent, as opposed to the North Pole, which is an ocean. So this is solid land, and it's covered with ice. Again, about 4 kilometers thick. And you see the red and green areas where ice is currently melting. I don't have a progression, but it is frightening to see, if you look at this picture over the years, that this here is getting larger and larger because more ice is melting and coming in this bay, which is easily accessible. This is South America. So this is a peninsula here, as it were. And here is a big bay. And there are lots of stations with observation stations that monitor the current state of the Antarctic ice sheet. And there is evidence not only here, but also here. There are some stations, research stations here, as well as on the North Shore and the East Shore. So there is the evidence. As I said, if ice melts, in particular the ice over Greenland and over Antarctica, which sits on land, if that ice melts, it becomes water and it flows into the ocean. So here's the evidence. Sea level rise. So there are 3 curves on this plot. They all go up. This is sea level rise. It isn't much, but it goes up. Here is the mean surface temperature over the same period, which goes up and spikes and then comes down a bit, but it's still going up. And there's a third curve that's here called OHC. So if more carbon is released into the atmosphere, where does it go? Well, about half of it, of the extra CO2 that we release into the atmosphere, gets absorbed in the ocean. There are critters living in the surface layer that take sunlight and do photosynthesis. They absorb the CO2 from the atmosphere, and gradually it sinks to the bottom of the ocean, eventually. And because of that, oceans suffer what we call acidification. And the ocean absorb heat at the same time. And this is what you see. So we know exactly how to measure the heat content of the oceans. And if you do that over time, you get this curve, which is pretty reliable, which shows that the oceans take up more and more heat as well as carbon dioxide. So that's the evidence. If you want to look at simpler things, look at corals. The coral reefs, especially in the tropics, near Australia, in Indonesia, some Madagascar, you'll see that reefs that were healthy before, that had lots of wild fish and other critters, turns dead. Because the ocean absorbs CO2, that means acidification, and coral reef is very sensitive to the degree of acidification. If you put too much acids in there, the coral can't handle it. They die off, and that's what we see here. So this is the same spot taken before and after. These are all phenomena that we are familiar with. If you read the newspaper, you know that the hurricane season starts earlier, more hurricanes, more violent hurricanes. That's here. We know about wildfires because there is tremendous drought. There are periods, extensive periods of drought. Think of Australia for the last few years. Think of the Western US. Wildfires erupt all the time at the moment, and it's a very dangerous thing. People get closer and closer up to the forests, and a spark burns down thousands of acres. Drought is a phenomenon that we see all over the world at the moment, especially in Africa. The areas that used to be suitable for agriculture are no longer suitable for agriculture. And in other areas, there's rain. That's the last picture here on the right. Especially in Southeast Asia, the monsoon moves in time as well as space. So the monsoon lasts longer, more rain drops down, and the monsoon moves regionally. The pattern of the monsoons is shifting. So you have floods where you didn't have floods before. So there's plenty of evidence that climate change is real. The cause is obvious. At this point, scientific community at least agrees that it is the concentration of greenhouse gases in the atmosphere that causes climate change. And why are there more greenhouse gases in the atmosphere? Well, that's human activities. We are releasing carbon dioxide into the atmosphere because we are burning fossil fuels. I showed you some of the effects. The global average temperature is increasing. The Arctic sea ice is melting. The Greenland and Antarctic ice caps are melting. Ocean levels are rising. Oceans are becoming more acid. These are all observed effects that are verifiable. Anybody who wants to check them can do that. And there are many anticipated effects on the weather. I told you climate is different from weather, but climate affects weather. We'll see more extreme events. We are seeing more extreme events. They're increasing in frequency, and they are increasing in intensity. We see changing precipitation patterns and extended periods of droughts. So these are the signals that we get, from which we can conclude that climate change is happening. And it's happening now, and it's us. Those are the three items that I want you to remember. It is happening, it's happening now, and it's us. Those are the three take-home lessons that you should pick up at this point and tell your friends. We know the main causes. I told you it's greenhouse gases in the atmosphere due to more burning of fossil fuels. And the phenomenon that we see, that the scientific community is discussing, is we seem to have entered a new geological period called the Anthropocene. If you look back pre-industrial revolution, climate was always changing, but humans could adapt. If there were periods of drought, as there certainly were, people could move around. So climate was a driving force for human migration, for example. Today, we as humans are changing the climate. That has never happened before. So this is a totally new phenomenon that brings us phenomena that we are not familiar with. And it doesn't look good for the future. What are the long-term effects? Well, one thing is loss of biodiversity. Certain species will die out, unavoidable, and it's already happening. It will be more difficult to produce food. It will be more difficult to get adequate water, certainly drinking water. So that increases insecurity. And in certain parts of the world, this is happening. Southeast Asia in particular, and Africa. So what we will see is mass migration. People move where they have food and water and the energy to produce whatever they need. So mass migration is not something that will not happen. It will happen. And we are seeing some of it already in Africa. In Northern Africa, people are moving north into Europe. And we see some of it here in the Americas too. And not only because of climate change, but the resulting political instability. If people have to move about to find food and water, that upsets the apple cart. Countries that used to be stable are no longer stable. And that is a real danger that we'll have to face in the near future. So therefore, we should care about climate change. So what is happening? What are we doing about it? A signal of hope came a few years ago, 2015, when there was the Paris Agreement. Think of it this way. We are coping with a global problem. It cannot be solved by local action alone. There's no institution in the world that has the authority to say what we should do. United Nations comes close. So the United Nations sponsored this Paris Agreement. This was the result of many negotiations that have been going on for several years. Finally, for the first time, there was a legally binding international treaty on climate change. It was adopted by 196 parties. COP is the Conference of the Parties at COP21 in Paris. That's why it's called the Paris Agreement. The goal was to limit global warming to well below 2 and preferably 1.5 degrees Celsius compared to pre-industrial levels. They set up a 5-year cycle where they would increase the goals, tighten up the goals for climate action. And the way to do that was voluntarily. Each country should determine what it would do to reach what climate action they would implement to limit climate change to 2 degrees or preferably 1.5 degrees Celsius. So this was a new mechanism that was designed because there was no authority. So people had to come voluntarily to some sort of an agreement. And this was what happened. Unfortunately, the US announced in June 2017 that it would withdraw from the Paris Agreement, which it had signed. Now there's a mechanism that then starts working and it takes 3 or 4 years. So the withdrawal became effective in November 2020, the day after the elections. But by executive order, President Biden in January 2021 announced that we would rejoin the Paris Agreement. So it's an executive order, which means it's not binding for the next president. Keep that in mind. So the last meeting was in Glasgow in November last year. And what happened? Well, there was a lot of reporting. Countries reported what they had, what actions they were going to take. There was lots of discussion about transparency. How do you measure what a country promises to do? How do you verify that? Financing was discussed. There was an obligation that $100 billion per year would be made available to help poor countries adapt to climate change. Well, the bottom line was it was all talk and no action. So we lost momentum for various reasons. The coronavirus pandemic was one of them. Later than the war in Ukraine came over us, and things don't look good. At this point, the scientific community expects that the temperature will increase by 2.7 degrees Celsius. So the goal of 2, let alone 1.5 degrees Celsius, is unattainable. 1.5 definitely is off the table. We can't reach that. 2 if miracles happen, we may be able to limit it to 2 degrees, but people expect, the scientific community expects that it will be probably closer to 2.7. So what does that mean? Here is the same graph that I showed you earlier, the Keeler curve, right? Here we are in 1958, it started, here's where we are today. And you can see the increase was 1 ppm per year in the beginning, 1.5 ppm in the 60s, 70s. It went up to 2. So the increase was increasing, as I told you. Now we're here. This is what we need to do to limit to 1.5 degrees Celsius. So we have to reduce the increase from 2.5 ppm where we are today to 2, then to 1, and then to 0. Once we reach this, 2030, 2035 maybe, then the CO2 concentration in the atmosphere will start decreasing. And by 2058, it will be at 435, I believe. So given that we have been increasing so far at an increasing rate, it is unlikely that we'll meet this limit by 2050. That's why I say 1.5 degrees is already off the table. 2 degrees, which would require this, essentially this curve, is maybe feasible, but it requires essentially a miracle. So we won't make it. 2.7. So what effect does that have? Well, here are 4 graphs that represent the heating that will take place in the next few years per degree Celsius, roughly. So the baseline is 1850 to 1900. This is one degree warmer observed, and this is how we simulate it. So there are big computer codes that we can use to explore a scenario. Suppose we limit our CO2 to so much per year. What will be the effect of the temperature of the Earth? And this is what the computations give us, and this is what was observed. So we are well beyond that at this point. If we go 1.5 degrees Celsius, which is probably not feasible, it will be a little warmer, especially at the North Pole, especially here, and the South Pole. If we go 2 degrees, which is the goal, right, it will be pretty warm in Northern Europe, in the Arctic, sorry. The Arctic Ocean will probably ice-free at that point during the summer. If we go beyond that, 4 degrees, look at what happens. It will be really hot in some parts of the world, so hot that people cannot work outside anymore. Think of the Middle East. Construction workers in the Middle East will have to find another way to do their job, because during the daytime, it's impossible. Your body cannot handle that kind of heat. So that's only one of the consequences. There are many more. And I think we all agree that this is not a good situation to be in. We are facing an existential crisis, just like this polar bear. And this is my final slide. I hope we will not get into this situation like the polar bear. Thank you very much.
Hans, a sobering presentation, and filled throughout with important information for us. So thank you. I think I need a glass of wine, but I'll hold that for later.
Now after the Q&A, I'll be happy to answer questions.
Please. We did have one question come in earlier to Vernita, so why don't we get started with that, and I'll paraphrase it for you, Hans, and we talked about it right before we got started here this evening. It was basically a neighbor asking what kind of impact people in the neighborhood are having with putting stones in instead of having gardens, and paving things over and runoff in the area. And Dr. Kaper said, well, we have that issue throughout the world, not just in Georgetown. So any comments on that generally, Hans? And then maybe, I don't know if you can translate it all to Georgetown for us.
Yes, well, as I said, it's not just a problem in Georgetown that people are replacing grass by concrete or what have you. Parking lots in the suburbs, it's a famous phenomenon, right? As I told you, the definition of a suburb is very simple. A developer moves in, cuts down all the trees, builds the houses, names the street after the trees that have been cut. So this is an extreme point of view, but that's a dangerous point of view because grass, come back to the original question, grass helps absorb water. It stimulates growth of trees, which absorb the CO2 from the atmosphere. So in principle, bio stuff is better than dead stuff. At some point, we'll have to rethink our cities, and better sooner than later, because we are spreading out and covering land that should not be covered. It's not a good idea to the water. Think of the water runoff, right? All sorts of junk that is in the streets today will run when there's a storm. It will flow off into the rivers, and God knows where it goes from there. Think of the plastic that we're all generating, right? There is now a plastic island in the Pacific, and another island is growing in the Atlantic. And these are plastic islands, not just natural islands. So this is what is happening today. We are careless with our environment. And we have to be much more conscious of what is good for the environment. Now, the worst thing, of course, it's not only Georgetown. It's, as I said, it's everywhere. But the worst thing is happening in Brazil. The woods, the forests in Brazil have been there for millions of years, and they play an essential role in the regulation of climate. As I mentioned in the beginning, climate is the system that tries to establish an equilibrium. And you need trees to absorb the CO2 from the atmosphere, even the natural CO2. And what is happening is that the forests in Brazil are disappearing. Why? Well, there's pressure, public pressure. People want food, so they need to produce more food. Okay, there's nobody around that sees that. Clandestinely, they cut forests and plant whatever they think will bring in money. Oil extraction in the forests in Brazil, it's another disaster. We are changing the land use. And the land, the way we use land is an essential component of the climate system. Think of it this way. If there's vegetation, you have cover, sunlight is shielded, so on the ground you can grow things. If there's no vegetation, no trees, nothing, it's barren, you'll get desert. And there are signs that lots of areas that used to be forested are changing into desert or desert-like areas. So that's not a good idea. We have to be much more aware of what we are doing to the environment. And keep in mind that we are guests. The environment was there before we were. So we are the intruders. And we don't have the right to dominate other species. That's what we have to keep in mind. So whether it's replacing grass by concrete or whether it's cutting down trees and forests, we are ruthless in pursuit of what? We have to ask ourselves. Okay, Carol.
Okay, thank you, Hans. The next question has come in, and I'm going to piggyback my question on this one. It comes from Alex, to everyone, and in the chat. And let me say, feel free if others would like to chat. I am reading it for Hans, or you can certainly raise your hand or unmute yourself and ask your own question. So the question is, how much will sea level rise if we keep to the 2.7 degree rise? Will Georgetown be covered in water? And my piggyback question is, I have a second floor condo in Bethany Beach. Should I be selling to someone who's not on this Zoom?
Okay. How much? 2 degrees? Well, it's not uniform around the Earth. Some places will see a bigger sea level rise than others. Certainly the east coast of the US is prone to being flooded at some point. We see this already in the Carolinas. The sea level is rising, and the houses that have been built too close to the beach, they'll fail. They'll fall down. A hurricane. It's not just that the sea level rises, but if a hurricane comes, the sea gets swept up, and it gets closer to land, higher up. And if your beach house is next to the beach, it will collapse at some point. So about Georgetown, yes, the Potomac will have an effect on the Potomac. Probably not much, but the danger is always the storms that come in, that will sweep the water up and up inland, and how far will it get? So when we talk about sea level rise, keep in mind that it's not just the sea level rising, it is the hurricanes that come with it. They also increase in intensity and in frequency. So altogether, you create a dangerous situation. I don't think, well, I live in Georgetown on Reservoir Road, which is high up, so I don't worry about it, fortunately. But the people who live next to the river, as we can see at the harbor front here, every once in a while, they will see more flooding. So the floodgates will have to go up more often. If you live on the second floor in a condo, it depends on where the condo is in Bethany. If the condo is right to the beach, I would sell, even on the second floor.
Thank you, Hans. I'm a half mile back.
Oh.
So maybe I have a few more years. Are there questions that someone would like to chat or unmute yourself and ask yourself? Please feel free. Hans, while people are thinking of other questions, and this becomes a question also of national interest and national defense. I keep reading articles about how, you know, the Russians really have populated the Arctic with a lot of sea cruisers, and the United States is lagging badly, and that a lot of natural resources will be unleashed depending upon what kind of warming there is. Do you have any comments or thoughts on, you know, national security matters among nations as a result of this?
Well, yes. So climate change is a real threat for national security. I'm convinced of that in several ways. I already pointed out, we'll see climate refugees, and we'll see instability in countries that are suffering, directly suffering from climate change. The Arctic will be open in 2050. We expect that if things continue as they do now, the Arctic will be open a good part of the year. So the resources will become accessible. And I have no idea how the politicians approach this, but it's a political matter. It's not something that you and I can discuss here over a Zoom session. The political will needs to be there to come to an agreement. And if that happens, we may be safe for a while. If it doesn't happen, and the invasion of Ukraine shows us what one of the parties is able to do, we better be prepared. It's in our national interest to make sure that people come to the table, and it's in everybody's interest. But if people refuse to come to the table, we have to be prepared for the worst.
Another sobering answer. Thank you for being so realistic. Diana has a question in the chat. What caused the big spike in sea temperature around 2016 in one of the graphs?
I don't know.
Okay.
Honestly, I don't know. Usually you can identify these spikes with some phenomenon. I didn't point this out, but if you looked at I showed one graph, the temperature profile from 1000 to today, and there you could see the little ice age that happened in the 14, no, this was the other slide, one that showed, no, that was the slide from 1000 to today. And in the 14th, 15th century, there was this little ice age, and you could see clearly there was a dip. So what exactly happened in 2016, I don't know.
And Diana says, no worries. Thank you for your answer. Anybody want to unmute themselves or chat another question?
Let me come back to that question about sea level rise. How much? So the question was, if we restrict us, if we limit ourselves to 2 degrees Celsius increase, how much will the sea level rise? So that will be, it will be measurable, but it will be of the order of a few inches, let's say. If we don't do that, if we let the CO2 level in the atmosphere go up further, and maybe we reach 2.7, maybe we reach 4 degrees, then we don't quite know what happens, because the ice that is on top of Antarctica and Greenland, those are the deciding factors then. If that starts to melt, and everything would melt, this will take a long time, by the way, but suppose that all the ice will melt, then you're talking about several meters sea level rise, several meters. So multiply that by 3, you get the number of feet. Certainly Georgetown down by the river will be flooded, no question about it, but that will take a long, long time. Ice does not melt so quickly. What will happen is that the soil underneath the ice sheet will melt, and gradually the ice shield, the ice shelf, sorry, on top is held back by certain ridges underneath in the soil, and those ridges will give way. That's the problem. So all of a sudden you get the formation of a big iceberg, as it were, that slides off into the ocean. And that's what we are seeing in Antarctica. We don't see that so much in Greenland, but in Antarctica especially, there are humongous sheets of ice that break off, and they can be as large as a state of the US, a state of Delaware, even a larger state like New Jersey. These are icebergs that contain a fantastic amount of water. And when that melts, it will take a while, but it will melt, then the sea level rise will be noticeable.
I have another question for you here, Hans, and it has to do with what individuals can do to help on this front. Eat less meat, you know, I mean, what can we as individuals do here?
Eat less meat is a good piece of advice.
Okay, well, that's
why is
generally.
That? So why is that? No, let me explain a bit. Beef production is very energy intensive. To produce a pound of beef, you need 10 pounds of feed. To produce 10 pounds of feed, you need 10 times 100 pounds of fertilizer. And where does the fertilizer go? It flows out into the ocean. It pollutes. So eating less beef is really good for the environment. So instead of eating 7 days a week beef, I recommend reduce it to 5, reduce it further to 3, maybe 2, and you will help the environment. Okay, now what else can we do? One of the big contributions that you can make is don't travel. Don't take air travel in particular. Air travel is very polluting. It spews CO2 into the atmosphere. And yes, you can buy, what do you call it, credits, carbon credits, I think they call it. But that's fake. That's just theater. It doesn't help, because you have no idea what will happen to the money that you give. Maybe they'll plant trees. How long does it grow? How long does it take for a tree to grow? 10 years, 50 years, depending on the tree. So you get no immediate result. And what we need is immediate action. So all these glamorous things like carbon credit when you travel, it's fake, it's theater. Less travel would certainly help. There are other things you can do, driving less. I've given up my car. Living in Georgetown, you don't need a car. You have good public transportation. There are lots of taxis. There's Uber, there's Lyft, you name it. So you don't need a car. That helps. What else can you do? It's difficult to point out specifics because individual actions, well, you can, the one thing you can do is, unfortunately, we don't have a congressman, but contact your representative and urge and point out where the problem is. Point out that politicians need to take action. So if you know a politician, you have to go outside the district for that. But if you know one, make them point out what the problem is and make them aware of it and urge them to take action, to join, for example, the Paris Agreement, be active, take a leadership role, what have you. And there are lots of good organizations that do good work for the environment. Some are better organized than others, but anything that helps biodiversity, I would say go for it. So at an individual level, this is not an individual problem. That's the difficulty. It's a global problem, and individual action doesn't do it by itself. You have to do collective action, and that happens usually only at the political level. So we have to influence our politicians, the decision makers. You can tell your stockbroker, well, I don't want to invest in oil companies anymore. That's another way, even though it's difficult to extract you from that. So there are ways, but they're small. But the big thing, the big steps will have to come at the political level.
Well, Hans, we're pushing up against our normal endpoint around 6:30, and I think that's a wonderful summary statement of action at the collective and individual levels. So why don't we end it there? And thank you so much for, as I said, a sobering but tremendous presentation on where we find ourselves in this particular crisis. And in addition to thanking you, I wanted to thank everybody for joining us this evening and also mention our next two events. On June 1st, we have taken tickets. We will host you for the canal ride, and that's been publicized for volunteers and for members. Feel free to contact the office for June 1st, 4 o'clock, the new barge down on the canal. And then we'll pick a place afterwards to gather and congregate and have a glass. And then also the next day we have a new member lunch. Please feel free to sign up for that if you've joined Georgetown Village during the pandemic. That's our definition of new members. We were trying to bring people together again in person, and that will be outdoors. Both events will be outdoors. Okay, thanks everybody, and most especially thanks. We'll give you a round of applause, electronic round of applause.
Thanks, Hans.
Thank you. Thanks, everybody.
Okay, thanks. We'll see everybody soon. Thanks for joining this evening. And thank you, Vernita.